Good afternoon, ladies and gentlemen. Thank you for attending Improving's December 4th virtual lunch and learn. Before we start, I want to inform you about a feature in the presentation that will make the session more interactive. Please make note of the question mark icon at the upper right of the presentation screen. Clicking that icon will open the question and answer feature, which allows you to send the moderator questions to be delivered to our insightful presenter at the appropriate time. Speaking of insightful presenters, I am proud to present Devlin Liles, who is president at Improving Houston. Today, Devlin will be sharing a webinar titled Data Access Then and Now. The floor is all yours, Devlin.
Thanks, Shervin. All right, so we're going to dive in kind of the history and the future of data access. So if you've never met me before, this is me. It's good to meet you digitally. This is just about everything you'll need to know about me. I am a passionate learner, and so if you've got questions, insights that you want to contribute, please. I definitely use that Q&A session icon in the upper right, and definitely dig into this. We definitely want this to be a conversation, and so we'll be pausing for different kind of questions, etc., as we go through this. So when we talk about data access, we're going to be talking about kind of three primary goals and structures when it comes to data access: the storage of data, its retrieval and usage, and then analysis. We separate analysis from retrieval primarily because of the size and scale of the data that's retrieved for analysis differs from the data that's retrieved to interact with a system or to affect change. If I'm looking at, let's say, every ticket sold in the United States for air travel for the past year and a half to identify trends, it's going to be a very different kind of interaction with our data than if I'm looking for what flights are available next week. And so that's why we separate those two, is those different concerns actually cause different interaction patterns. Now, when we look at this over time, it's good to know where we've come from, because data access and storage systems and those kind of things very much are like any other part of software development, in which we are building on the lessons of the past and oftentimes having to relearn those lessons. So we really start in kind of the 1956 to 1962 timeframe. And there are a couple of big things that happened in this. One is kind of logical table storage, the invention of the first hard disk, as well as IBM building the Sabre data storage system that actually was there to help American Airlines to track flight reservations. And these were really the kind of burgeoning front end of the data access and storage systems. Before that, you had some tape drives and you had punch cards and data analytics, but data was transient. Like storage of large amounts of data and the ability to infer business information from that was really a kind of a new advent in the 60s. And then in the 70s, you had, COD published this great article about relational databases and how interactions between data could be structurally independent from how the data was stored. The idea of a logical schema versus a structural schema was really a revolution, and it became the kind of gold standard for interacting with data for the next 40 years. From that idea of relational databases came Ingress and System R, and so Ingress had QUEL, and System R used SEQUEL. Now those are where we get the term SQL, but is not actually SQL or structured query language. Those two have kind of blended over time, but that was the original portion of this. And then kind of later on, the introduction of the entity model, so ER models or entity relationship models, of the ability to kind of talk about and structure independent of the way that data was acquired and stored, and designed for an application of data. And so this is where a lot of our entrenched beliefs around data storage and interaction come from. The idea of stored procedures and interaction with data being the primary function of an application, CRUD operations. All of these things came through that design structure in the 1970s and 1980s. But we started to see a shift in that in the 1980s, where the SQL structured query language became a standard, and you start seeing ISO SQL and ANSI SQL and these kind of things, and PL SQL and certain variations, but all of them kind of building off of that SQL standard so that relational database management systems could work towards a common interface language. We also started seeing the advent of high performance systems. So systems that were meant to help with manufacturing, execution, real-time measurement. And we started to see a differentiation in how they dealt with data versus the relational data storage. And high performance data systems started using things like ladder logic and register access, and then funneling those into SCADA systems, or service control and data acquisition. And the SCADA system started pumping data out of those high performance systems and into relational databases for more operational reporting, for the ability to interact with and see data that was moving through some of these high performance systems and be able to operate on it. And then as we continued into the 1990s, we started seeing more and more local applications, with .NET coming through in the late 90s, and VB and Power Builder, and a lot of these applications that were harnessing the growth of processing power in the PC. You started seeing Excel and Microsoft Access and Lotus 1-2-3 and all of these applications that started putting data in the hands of users, but putting it in the hands of users with local processing power. You no longer needed these giant systems that were sitting in a warehouse somewhere or a data center somewhere, really crunching through those numbers. You could do some of that numbers and analytics crunching on the machine itself. And so you started seeing the ODBC connectors and those kind of things show up in this space. And then we hit the 2000s, and the 2000s were really the renaissance period for data acquisition. We started gathering data at a monumental pace. Data acquisition massively increased, orders of magnitude increased worldwide during the 2000s. And we started seeing things like big data. Now, big data was originally used to talk about systems of data that traditional tools could no longer deal with because of the size of it. And we're at this point in time, we're talking about only a few players. We're talking about the indexing and search algorithms of some of the large search firms like Google and Alta Vista and those kind of things, if you remember back that far. But we're also talking about like sales data from Walmart's Teradata network, or American Airlines' evolution of Sabre and becoming a clearinghouse for like global reservation systems, those kind of pieces. But at the same time we were seeing this consolidation of large sets of data, we were also seeing a movement in tagging and enhancement of that data. So not only did we want the transactional data, the operational data, but we wanted the context by which it was generated. Did this data come through one of our sales channels? Okay, tag that onto it. Did this data come in real time, or was it batch loaded? Okay, tag that detail. Hey, this data is related to products. We're going to enhance it with product data as we get it into our data warehouse. And so you start seeing this burgeoning data warehousing structure of data storage, enhancement, collation, and really trying to create a source of truth. We'll dig into that here in a little while. And then in the early 2010 space to 2015 really was the driving force for the NoSQL movement and document storage, as well as more automated analysis and predictive analysis of, now that we have all of this data, what do we do with it? And so as we talk through this, when we walk this evolution, you're going to see pieces, even in today's world, in which every one of these evolutionary steps still brings value to the table today. But the first thing that I really want us to dig into is the storage of data. Now, originally, we started by storing files. We created a digital representation of the physical construct. Ironically, nowadays, you'll hear the term digital twin used often. But we really did represent computer systems in this digital space. And they were replicas of the physical space that we were dealing with. And one of the reasons for that is it made it easy for the users to interact with this new digital medium that they'd really never experienced previously. When you're starting to talk about the virtual space and cyberspace, it invokes a lot of imagination, and we had no real way to discuss and to transition these things. And so one of the things that we did was we represented files and folder structures and hierarchies, and that allowed us to store and sort and organize these things. Now, unfortunately, what that meant was that we actually had to know what we were going to store ahead of time. We had to know what folders we needed. We needed to know what cabinets we needed, these kind of things. And so we had these very explicit languages that really had to know, all right, here's the data, here's the columns, here's the records that I'm going to go create. And so you'll see SQL here as an insert statement, right? Now this has evolved over time so that the computer has gotten smarter about tracking the changes that the system makes. So that now using object relational mapping or ORMs, we're able to go, hey, save the changes I just made, rather than in our communication with the data storage system, we don't have to enumerate those changes again. We can simply make those changes to objects or documents or whatever representation we use, and then commit those changes rather than having to re-enumerate them. And we look at this evolution, we go, all right, why have we been able to do this? One piece of that evolution has come from the increase of processing power. The processing power of my cell phone is actually a lot more than the processing power of all of NASA when we put somebody on the moon. And so when we look at the power that has been brought to the common PC, it's more powerful than supercomputers were in the 80s. So we have the ability to track a lot more information, keep it a lot more in memory, but we also have the ability to store a lot more. In 1960, the image on the left is actually a 5 megabyte hard drive. The thing was the size of 2 very large washing machines and weighed several hundred pounds, took a lot of people to move, and IBM was at the forefront of this. Now, if you look at the forefront of this, you find folks like Seagate, Corsair, and SanDisk. This is Seagate's, the 18 terabyte drive is the largest, commercially available drive that's not special made. But then you also have things like the 8 terabyte solid state or the 1 terabyte micro SD that is, the size of my thumbnail, but holds a terabyte of data. So our ability to store and transfer data is impressive. And so when we look at what we would have defined as a lot of data previously, right, a lot has changed since this 60 years of evolution. And in that 60 years, we've had to kind of come up with new ways to describe change. One of my favorite ways to represent this, and unfortunately I don't remember where I read it, but it was a great way to talk about it, was in orders of magnitude. Now the numbers always change in this, but the perceptions, the subjective measures don't, right? A small database is one where you don't have to worry about speed. The tools by themselves will be fast enough. Typically, this means you're dealing with about 100,000 to 1 million records. A medium-sized database, you got a few problem tables, you got a few problem objects or documents, right? 1 or 2 people on the team, part-time, typically handle that. Not a big deal. You're dealing with 1 million, 10 million records. And then on the large databases, you're talking about, this is somebody's full-time job, is to monitor, enhance for performance, help design for performance. And then this is where you're getting into the hundreds of millions or billions of records. Right. And then on the very large side of it, you've had to write software to customize performance on the fly, to design performance, right? Designing performance first and foremost, right? This is tens of billions to hundreds of billions to trillions of records. You're in this space. Now, most of us actually don't talk about the software we have to write for performance like this. We talk about it as archival strategies or data warehousing strategies, or we talk about it as, sharding of databases and those kind of things. But that is all the things that we would do when we're approaching this large and very large structure. And we're typically planning for the future. Now, very rarely are we ever actually having to deal with we're going to store so much data that we don't have hardware to store it on, right? Whether that's us using the cloud or whether that's using our own hardware on-prem or some combination, the ability to acquire hardware to store enough data in this space typically isn't the problem. Even if I'm storing petabytes of data, the acquisition of hardware is not a limiter the way it was at certain points in that evolution. When you talk about the late 60s, getting hardware to be able to store large databases or to be able to combine multiple databases was very difficult because of the size of storage. When I look at the late 80s, early 90s, we hit another hardware winter where the storage on disk was slow, and it was just not big enough to deal with some of the problems that we were trying to tackle. And so we go through these oscillations when we talk about data storage of the processors will get faster and faster and faster, which means our applications will be able to take on more functionality. And then we will end up storing a lot more data. And then the data storage systems will need to get faster and to get bigger. And then that will free us up to go pursue more and more processing power and more functionality, more enhancement of data. Right now, we're in that cycle in which data storage and speed, not the problem, right? We're typically talking about the ability to intake data in concurrency. We're talking about functional ability to enhance data, to bring together multiple data sets. We're not talking about, I can't get a hard drive big enough to store that, because the technology has evolved to the point currently where that's not a problem. When we start talking about like digital records for a human being from birth to death, we might get back into a space that data storage becomes a problem again. But the price of a gigabyte of storage has been dropping for years and is basically bottomed out to hardware cost at this point. So when we talk about the retrieval of data is a complexity that is enhanced by our storage of that data. And so very simple systems is where we started. We started with effectively the digital version of the Dewey Decimal System or the card catalog. We started with the idea that, well, we'll just keep a separate file that is the kind of roadmap to where to go find something. And whether this is your partition table on a hard drive, or whether this is your indexing system in your database, we still do this today. We do this with compression in how we actually allow redundant data to be compressed out of a file, is by keeping a separate place that says, here's the map to redundant data. Now, we run into a constraint that is actually based on the math of this problem. And so to talk about it, there are two very common analogies when we start talking about the retrieval of data. Typically, speed of write is a storage concern, but speed of read is a retrieval concern, because they approach the problem differently. There's more data that you want to enhance, etc. And so when we talk about this, there's kind of two analogies that'll make this easy to grasp. The first one is, if I take a standard deck of cards and I want to find a specific card, if I just have a random pile, I shuffle it, it will on average take me half the deck, if I do this enough times, to find the card I'm looking for. So 26 cards. Now, if I were to divide that deck into suits, if I were to index by suit, I would then pick which, like, imagine all the cards are face down, but I've got 4 piles in front of me, right? I flip over the pile with hearts in it and I keep going. So I pick the suit, right? Which will take me 1 to 4 random flips, because I'm going to flip over the first one. So we'll say 2 on average. And then I'm going to scan through those cards, and it's going to take me about half of those on average. And so now I've been able to reduce the number of times that I had to flip over a card or search through a file for a specific record from 26 on average to 9 on average. So when you talk about like sorting algorithms, right, best case is you only have to look at it one time. You flip one card and it's the 8 of hearts. That's what we're aiming for, but that's statistically not possible all the time. And worst case would be it's the last card and we have to flip over all of them and it's 52 flips. That's statistically not very likely either. And so you get into things like RDX algorithms and MDX algorithms that sort and filter data so that you can get as few flips as possible, or that average best case for certain types of searches, right? And so when I do those types of searches, I use those algorithms. Now, the good news is our data storage and retrieval system, SQL Server, Azure, Documents, Mongo, Raven, kind of all of them out there, Cassandra, Couch, you can keep going. All of them have started to add more and more of these specialized pieces in their query engine so that their query engines can get more and more optimized towards that best case. Now, in a deck of cards, 52 cards, it's pretty easy to brute force this given the level of hardware that we're dealing with on a day-to-day basis now. But imagine a phone book. Now, for everybody that's younger than I am, a phone book is like Google for phone numbers. It used to have a list of everybody and their home phone number. That is a mobile phone that is connected by a cable to the wall when it's not charging. So in there, it's indexed for a very specific type of searching. It's actually using kind of a, when I search through a phone book, I can search with kind of a binary decision tree. If I'm looking for somebody with a last name that starts with a J, I'm going to split the phone book basically in half because it's alphabetical and I know that. And then I go, oh, all right, I'm at O. I'm further than I wanted to be, and I'm going to go a rough estimation of how far back I need to go. Like, okay, I'm past H, but I'm before L, and it splits the number of sorts that I need to do. And then inside the page of data or the page in the phone book that I'm looking for, I find the single record that I care about, and there's a phone number attached to that. Now that works incredibly well if I'm going by the last name of the person, which is how phone books were organized. But imagine you're looking for a specific phone number. You'd have to flip every page in that phone book because that's not how it was built to be searched. Data storage systems are the same way. We have to know how we're going to search the data to be able to find it effectively. And so you'll hear the term index, and that brings in how am I going to search the data, right? In the relational database world, you'll actually have a clustered index, which means that the data you're looking for and the key you're looking for it by are stored in the same place, right? The phone number and the name are right next to each other, right? Or non-clustered indexes, which are, I'm going to keep a card catalog like the Dewey Decimal System, and it's going to tell me where to go look for the data, but the data is not going to be there. The book's going to be on a shelf somewhere, right? And so you see these kind of physical analogs to the way we search through data. Now, this is an interesting thing because when I'm talking about like Dallas-Fort Worth, we're talking about 4 million records. You know, you remember when I talked about defining big, right? 4 million records is a medium-sized database nowadays. Could you imagine trying to find a phone number in a phone book that held 10 billion records, right? You wouldn't actually be physically able to turn the pages. The thing would be mammoth. And so we have similar problems when we start talking about data retrieval at that scale. And so indexing algorithms have had to evolve over time as well. And when we're searching for data, the retrieval of data at this low level matters a lot, but so does the way we approach writing the software. Because if I'm going to pull a bunch of records in memory and sort them in memory, or am I going to ask my database engine to do that for me? Database engines are typically much more optimized for this type of searching than a record by record review, the way an application would typically be written. And so as we look at retrieval of data, we need to understand the underlying portions of how that's evolved so that we can bring the right tool to the table. Now, if we look at the kind of analysis space and the evolution of that analysis, it actually goes way, way back, long before the 1960s. In 1865, the Cyclopedia of Commercial and Business Anecdotes was published. And inside it, Richard Devens talks about manually going and acquiring data and crunching the numbers and being able to beat his competition because empirical evidence-based management was a way to drive business. Now, that idea of applying data into a business is not new, but that's what we call business intelligence. Now, this all took a kind of a massive leap forward in the 1960s when we started applying these to complex problems that computers were able to help us find new patterns. Now, that's what the picture in the middle here is actually the 1962 midterm elections. We were crunching some data on exit polls and these kind of things, and there was some really cool R&D going on around data analytics and business intelligence that ultimately had some strategy recommendations of like, hey, this issue, if at the time Senator John Kennedy would take this position, he could probably turn these voters, and that might make him beat Richard Nixon, and inevitably he did. And so there's some great books. This is actually a photo from the New York Times on that evolution and the data that was applied in this space. And so we've gone from kind of basic understanding of this and applying a lot of people. Something I'd like you to notice in the middle photo here is there are more people than there are computers in that room, because the analysis of data has largely been a human concern up until the last 20 years. Compiling the data was the computer's job with the advent of computing. But the analysis was a human being's, because we had intuition. We could read between the lines. We could notice patterns that the computer couldn't notice. But then we started building these data warehouses, and we started building these large compilations of data, and computers got smart enough through the acquisition of processing power and new programming languages and things like machine learning and Python and TensorFlow. Computers got to the point where they could see patterns too. Now, we had to tell them what to look for, and we had to train them, and we got into all of that. But we started being able to have these sources of truth in which we would go to, these data warehouses, and we would write these reports looking for specific types of patterns and specific patterns, and we'd report on them so that the analysis, the number crunching, was no longer a human being doing that work, but the computer was doing it for us. And then humans were interpreting that to take action. And that's actually where kind of the evolution for AI and machine learning and all of that comes in, is that we originally start with data collection and storage. We have to go acquire data, and we have to store it on disk somewhere that we can access. And then once we've got enough data, we start looking for exceptions, and we start reporting on those. Like, hey, this sensor was offline for these 5 minutes yesterday. Go have a maintenance person go look at it, please. And when we got that reporting, then business intelligence would look at it and go, hey, it turns out those sensors go out a lot, whereas these other sensors don't go out as much. We should move all of our sensors to this other brand because they don't go out as often, and it'll save us some money. That's exception reporting into business intelligence. All right. But then the jump into artificial intelligence, the machine itself looking for ways to do that, is going, hey, we don't know which brand works well, but I'd like you to go analyze all of this and test out some conclusions, and I'll tell you if you're right or not, right? And the idea of general AI it's been around since about the late 1960s. The idea that we could teach machines to be like humans and be these multi-purpose machines is a lot like general robotics. The idea that we can build a robot that can do all the things a human being can do. Now, right now, that's not technically possible, the same way general AI is not technically possible, in that we have started building these very specific and targeted machines. We can build a robot that runs faster than a human, but they can't also play the violin better than a human, right? So like, we build ones that can do something very specific because it makes the problem space a lot smaller. We took the same approach with AI, and we taught them very fine-grained small problems. And once we had solved that, we then use that to build to the next problem. And this is where you get into neural networks and those kind of things. Now, the hype is not new in this space. I took and just graphed exponential to linear progression. And within 10 years, a digital computer will be the world's chess champion. And within 10 years past that, a digital computer will prove new mathematical theorems. Machines will be capable within 20 years of doing any work a man can do. Within a generation, the problem of creating artificial intelligence will be solved. In 3 to 8 years, we'll have a machine with the general intelligence of a human being. Now, these sound like I ripped them straight out of the headlines today. Unfortunately, it's from 1958, 1965, 1967, because the progression of AI is an exponential growth problem. It's going to be disappointing for the vast majority of the timeline. But what we're looking at today is being in the inflection zone based on industries. The milestones are not of new paradigms. The things we're seeing are not new ideas, but simply computing catching up with old ideas. In 2005, an autonomous car drove 131 miles by itself. In 2007, an autonomous car drove 55 miles of urban streets with no incidents. 2011, IBM's Watson wins at Jeopardy. We are in that inflection zone. There are times when computers are really dumb. Like when we first tried to teach them how to walk on 2 legs, the computer's answer was, if I need to go 400 meters, I need legs that are 500 meters tall and I'll just fall over. Kid you not, that was its actual answer. So we had to teach it a lot of things that you really never would have to teach a person because of physical constraints and intuition and these kind of things. But we're in that inflection point now in which the computing ability is actually catching up with some of the hype from 60 years ago. Now, in that 60 years, we've added a whole lot of new hype. All you have to do is open up Twitter and you can see all of the great things that AI is, quote, going to be doing in the next 10 years. So I would approach this with a word of caution, because we've talked about data storage, we've talked about retrieval, and we've talked about analysis. Those problems get bigger for machine learning and AI, not smaller. And our solutions have to get better. Because right now, if you talk to somebody in the data space around machine learning or artificial intelligence, they'll tell you that data cleanliness and the ability to get accurate, clean, timely data into a system is one of the biggest things that's hamstringing that industry. And they're right. And so where does this all lead us? Like, how do I stay ahead of it? I'm going to diverge a little bit and we're going to talk about video games, because I think there's a great lesson to be learned. Orthogonal implementation and orthogonal data usage and compilation usage and these kind of things is going to drive a lot. What I mean by that is things that seem disconnected being combined to great effect. In 1919, we invented the ability to injection mold plastic. In 1946, the idea for an RFID, or a radio frequency identifier, was proposed. In 1972, we created the first video game console. But it took almost 40 more years for somebody to combine those 3 technologies into Skylanders. And they sold over $3 billion worth of these little figurines that were injection molded RFID tags that the video game could talk to. Competitors then launched a whole lot of them. I think Disney ended up launching one and made over $1 billion on the imitations and the competitors. It took 40 years for somebody to combine very old technologies into a $4 billion idea. Why did it take so long? Well, it turns out the problems don't go away as we evolve into these new ideas. And so if you want to focus your skill set growth, you want to continue to stay on the burgeoning front of the data space, you're going to have to get really good at solving these problems. We talk about data storage and collection, right? Where's the data controlled, right? Where do we enhance? Where do we modify? Where do we control the data coming into the system? How do we synchronize multiple sources of truth? Because everybody's got a data warehouse nowadays. And if you don't have one, you have data marts, or you have databases, or you have file systems and Excel sheets that you're trying to bring in and pull together. Who owns the data is a question that we've really never addressed in the on-premises storage world. There wasn't a question of who owned the data that was in my database on my disks that I collected from inside my company. But what about cloud-based data? What about data sets I license from other organizations, right? Now we've got this whole new problem of like, who owns it? Are there restrictions on how we can use it? What's the cost of moving data? The highest bandwidth way of moving data around the world is still FedEx or UPS or DHL, because it turns out if I take those micro SD 1 terabyte cards and I put a ton of those things, literally a ton of those things, in a 18-wheeler or in a shipping container and ship it around the world, it will be faster than trying to transfer that amount of data over the internet. The bandwidth for FedEx is impressive. There's a great blog article about it. You should definitely look it up. It's entertaining. It turns out SneakerNet will still be a thing. But then also, how do we enhance, annotate, and canonize, or kind of centralize on a definition for certain data, right? When we have customer data, what defines a customer? What key attributes do we have to have? And then how do we store our calculations on top of that data and then use those calculations in future data? That's going to create a calculation bias. Do we use already calculated data and pre-calculated ideas, or do we go back to raw data? So you have to start managing this calculation bias as you get into second and third tier interpretations. Keep in mind, we're still at this point in data storage and collection. We've introduced a whole new set of problems in the reporting and expectations and exception management. Are we looking for known patterns or unknown patterns? Known patterns are pretty easy. Most of us are building applications today looking for known patterns, right? How do we integrate these into operational processes? The unknown patterns, right? We have exception management, but are we tracking and looking for patterns in the exceptions, right? Hey, it turns out that every time we run batch process for accounting in this system, because of the amount of network traffic it uses, it causes this other system to fail. If we move those two things into separate VPNs, we'll remove the failure. That's unknown pattern detection, but it requires a lot of root cause analysis and pretty heavy monitoring and telemetry that we typically haven't done. And that's where frequency of reporting comes in, right? Time-based or event-based reporting, and how do you merge those two things back together? The usability of that reported data, right? Dumping everything into Excel was a great answer for 30, 40, 50 years. It's not anymore, right? That usability of that data, we need to make decisions faster and we need to be more confident in them, which means I'm going to need to highlight that data. I'm going to need to boil it down into the actionable pieces that are pertinent while not losing the context of all of the additional detail, right? And then we start looking at boundary conditions and we go, are those volatile boundary conditions, right? I don't want this to get above 180 degrees unless the pressure is below this, and then that boundary moves. We start getting into some more of the stream analytics and real-time side of it. Alert delivery becomes a problem, right? If I'm talking about real-time analysis and issues, how am I delivering that alert to an operations person who might not be in front of their computer, right? This is SMS or dedicated alerts, or do I have to put sirens and klaxons and lights in an operational facility, right? Do I allow for boundary adjustment, either manually or automatically? Because we want as much signal and as little noise as possible in the data, which means that we've got to write systems that are smarter about how they deal with data, because we want to be actionable in the data versus seeing data in action, right? Data in action is great as a technologist, but it solves very few business problems. Whereas actionable data, being able to go, hey, here's a market condition that hasn't happened yet. We need to go, respond to it. And as you can see, these all build on each other. They all are driving us towards this idea that data skills are becoming more and more prevalent, because the panacea, the place we're all trying to get to, is this kind of predictive and prescriptive analytics space, right? We need to be able to look at problems and be able to kind of make decisions on them and look at the pieces around that problem, the context data, to be able to move them, which means that I'm going to start spreading out places where instead of assuming, I'm going to start measuring. One of these that I found very early in my career was that the inbound weight for a chicken at Tyson Foods was heavier on certain days, and I couldn't figure it out. And one of the ops guys goes, "Oh, it was raining that day." I'm like, "Well, how do you know that?" And he's like, "Because the weights were heavier." And so instead of assuming what the weather was, we started measuring it. And we pulled in a forecast stream for each of the locations. And when it was raining, we adjusted our idea of what was acceptable. And so as you question and run into those barriers, you're going to have to expand the footprint of data you're collecting to feed into those analytics engines. And that's going to mean more app dev and more data cleanliness problems and more storage and more exceptions. And so the problem space just continues to expand and get bigger. And then as we start monitoring these, we want to feed that monitoring back into the systems, or back propagate the data from saying, hey, the system's working well. We need to tell the system that so that it can go, oh, okay, I should do that more often. Or, hey, something went wrong, I should do that less often. So that we can kind of model for the things we know we don't know, without cutting off the things that we really have no idea that we don't know them. Ultimately, getting to that prescriptive analytics side of actually making an automated intervention, right? Either I'm going to tell a human to go do something, or I'm going to tell a system to go do something. And those require a lot more than just software, right? That's hardware, that's human intervention and override, but that's also a trust of that system and the ability to assess how we got there. Because if we were to look at the most valuable skill set to be growing over the next 5 years, it's going to be one of data access, data storage, data analytics, and the understanding of all of the decisions and evolutions that have come before. Because the decisions and the structure of how we built mainframes in 1960 and 70 teach us how we got to where we are today. And when we're interpreting that data, when we're enhancing that data, those decisions are important to understand. Right now, we generate roughly 2.5 quintillion bytes of data a day. That's the equivalent of 1.7 megabits a second of data for every human on the planet. Like, we're going to be using that data in crazy ways over the next 5 to 10 years, but it's going to be built on data analytics, data access, and the ability to do those things well. It means dealing with larger data than we've ever dealt with. It means storing more data than we've ever stored. And that could be using telemetry in insurance. You already see this. How many folks have an insurance company that gives you a little old dongle that you plug into your car and gives you a discount on your insurance because of it? Why are they doing that? What's that discount buying them? It's buying your driving data. It's buying how hard you're braking, how fast you're going, where you're going, what common places do you waver on your car? Are you heavy on the gas pedal? Are you heavy on the brake? It's teaching them how big of a risk you are for insurance so that they can average that to make sure their risk profiles are correct, right? The sales of houses and what houses sell quickly, what houses don't, what houses get renovated, what houses don't. Preferences and the data of sales in houses have changed the way we build houses, right? I mean, we kind of knew that bathrooms and kitchens really made the difference. But what if, through the analysis of all the sales data, I know that certain types of marble give me a 1 to 2 cent per square foot increase, but are cheaper than the stuff I was using before? I can actually start optimizing for sale and renovation in a way that the industry's never done before. We can start optimizing that experience. And then we take it to something more practically applicable today, using cell phone data and its telemetry and GPS to analyze outbreaks of a pandemic. That happened this year. They were able to do contact tracing using cell phone data. And so you start looking at all of these things. Data skills have never been more important to us. But if we're going to get good at it, we can't rely on the underlying systems to provide us with the answers. The idea that, oh, I'm using SQL Server, it'll solve that for me. That's probably true for the 80% case. But more and more, we're living in the other 20%. Salaries in data analytics, Python, machine learning have all been going up. Whereas kind of your standard data analysis, database developer jobs, the salaries have been going down because it's easier for those jobs to be more commoditized. So if you're going to invest, I'd invest here because this is where the industry and app dev in the future in the next 5 years is headed. So I do want to stop. I've been kind of pontificating through history and give Shervin a chance to chime in if there are any questions.
We don't have any right now, Devlin. I'm sure
Awesome.
there might be some in a few minutes.
So I'm gonna precede in one of my own, and then if there are no questions other than that, we'll kind of wrap it up and call it a good day. Where do you get started? So right now is a great time for this because Pluralsight and Udemy and a few others have given away a lot of this for free. Getting started with understanding Python and TensorFlow, Microsoft Cognitive Services, AWS, Google, all of them have options for this. Getting started in there, building some of the example applications, even if you don't end up going that direction as your primary skill set, understanding how those systems are built lets you structure and build applications better. It lets you address data concerns and data cleanliness issues because you know what the systems that you're going to feed are ultimately going to need. But start looking for the places inside your application in which the better answer might be to teach a system rather than build one. Things like logistics distribution for oil and gas, right? Traditionally, it's been rules-based, but what if it was machine learning-based? Or pattern recognition for DOT records for driver risk, right? Safety and incident tracking, behavioral safety, leak detection. There's hundreds of different little places in multiple industries that we can apply data analytics to get better answers on the other end, even if it's agile adoption, right? The ability to, all right, let's measure which projects benefit the most from Kanban versus Scrum versus single piece flow or XP processes, right? Those will inform better decisions going forward, and the data is fairly easy to track. Good news is there's a lot of systems out there. So if you're going to get started, I'd say take a data analytics course off of somewhere like a Pluralsight or a Udemy. Sit down and get into it like a deep dive. We had a working group that we analyzed baseball statistics to teach ourselves how to take that data analytics and machine learning approach. It'd be the easiest place to get started in this, and it's going to pay long-term dividends both for the applications you're building and for the future career of having a skill set that is definitely not going out of vogue anytime soon. All right, well, Shervin, I'm going to hand it over to you, and if we've got questions, awesome, let's go, and if not, I greatly appreciate everybody spending their lunch with us, and hopefully this was informative and valuable to you. Cheers.
Thank you, Devlin. Thank you all for attending today's virtual lunch and learn. And Devlin, thank you for sharing data access then and now. The recording of this session will be available the next business day. To view the recording, locate the session from Improving's virtual events page. While you're at the virtual embeds page, please make sure to register for future Lunch and Learn sessions. Join us on December 11th, where Chapman Betzel will be presenting Cypress, what it is and how it works. Goodbye and happy holidays.